Thank you very much for inviting me to give a talk. So today I will speak about joint work with Chantal David and Mathilde Lalin from Montreal. Almost all the results are joint work with them on certain non-vanishing results for L functions associated to cubic characters. So let me start with a little bit of introduction. A Dirichlet character is a completely multiplicative function. So if a character has modulus d, then it's defined on z modulo dz, things co-prime to d. It takes complex values and we extend it to z by periodicity, and it has the property that the character is equal to 0 whenever we have something which is not co-prime to d. And then we call the character to be primitive with conductor d if d is the smallest modulus for which chi is a character modulo d. So in some sense, the character doesn't come from any smaller characters. It's not induced from any smaller characters. So once we have the character, we can associate to it an L function. So when the real part of S is bigger than 1, we define the L function by the Dirichlet series chi of n over n to the s. And this has an Euler product, an infinite product over primes, 1 minus chi of p over p to the s inverse. It has a lot of nice properties. So for example, it can be analytically continued to the entire complex plane. And it has a functional equation. So we can relate L of S chi to L of 1 minus S chi bar. Chi bar is the conjugate character. Then a natural question that people care about is the L function vanishing at the point 1/2? So people care about non-vanishing questions. For example, the Burgeon-Swinnerton-Dyer conjecture relates the rank of an elliptic curve to the order of vanishing of the L function at the critical point, at the central point. So that provides a very strong reason for an L function to vanish. So then in general, there is a philosophy that says that L functions should vanish at the central point 1/2 for very special reasons, like being related to the rank of an elliptic curve. Now, if we look at Dirichlet characters, the conjecture, a conjecture due to Chowla, is that the L function should never vanish at the point 1/2, the L function associated to any Dirichlet character. So this was originally conjectured for quadratic characters, and it was later extended to any Dirichlet character. This is a very strong conjecture. We don't really know how to approach it for any Dirichlet character, but we can say something. For example, if we look at the family of L functions, can we say something about what happens with the L functions, with the values of the L functions at the point 1/2? So for example, if we restrict to some special characters, if we restrict to quadratic or to cubic characters, can we say something about non-vanishing at the point 1/2? Now, one way through which we can study this problem is by computing moments of L functions. So we consider L functions in a family and we compute moments in that family. So these are averages of powers of the L functions. And by studying these moments, we can often say something interesting about non-vanishing. So for example, if I restrict to the family of quadratic characters have been studied a lot because they are related to many interesting questions in number theory, like ranks of elliptic curves or class numbers. Then let's denote by chi d the quadratic character. Quadratic just means that it's a character of order 2. So the square of the character is the principal character. And what we're interested in is computing moments, so the kth moment of L 1/2 chi d. And here we are summing over, I have a star on the sum. This means that I'm summing over primitive characters. Okay, so we want to compute the kth moment of these quadratic L functions at the central point 1/2. For a long time, these moments were not that well understood. In fact, it was somewhat clear what the size of the kth moment should be. So it's not hard to see that it should be asymptotic to x. Here, the fundamental discriminant d goes up to size x. So it's asymptotic to x times log x to the power of k times k plus 1 over 2. But what's more interesting is that we have some constant ck in front, and this constant was not well understood for a long time. Then the breakthrough came with the work of Keating and Snaith, who used random matrix theory to model these L-functions. And by computing the kth moment over the unitary symplectic group, they came up with this value of ck. And they conjectured that it's the same constant that comes in this number theory computation. Now, in terms of rigorous results, a few moments can be computed, actually computed. So the first two moments are due to Utila in the 1980s. For the second moment, he had this leading order term of size x log x cube. But in fact, in the Keating and Snaith conjecture, that there should be some lower order terms. So there's a more refined conjecture due to Conry, Farmer, Keating, Rubinstein, and Snaith, the so-called recipe, that doesn't use random matrix theory, and it predicts that the kth moment should be asymptotic to a polynomial in log x of degree k times k plus 1 over 2. So we have lower powers of log. So in Utila's result, he recovered the leading order term, so the log x cube. And later work of Soundararajan in 2000 recovered the entire polynomial predicted by the recipe for the second moment, as well as for the cubic moment. And there's an independent, different approach using multiple Dirichlet series of Diaconu, Goldfeld, and Hofstein, and they recover Sound's result for the cubic moment. And the recent work of Shen gets the leading order term for the fourth moment, so the log x to the 10. This is conditional on GRH, and it's using ideas of Sound and Young, who worked in a different family of L-functions. So how can we use these moments to say something about non-vanishing? So if we directly use Cauchy-Schwarz, then we get that the number of discriminants d for which the L function is not vanishing at the point 1/2 is bigger than the ratio of the first moment squared over the second moment. And we know how to compute the first and the second moments. The first moment grows like x log x. The second moment grows like x log x cube. So this gives us a proportion of non-vanishing of x over log x. So this is an infinite family of discriminants, but it's not a positive proportion. We would like to say something like more than, let's say, c times a constant out of all these L functions are non-vanishing at the point 1/2. And it turns out that one can refine this moment method using mollifiers to show that we do have a positive proportion of non-vanishing. So this is a result of Soundararajan, who computed the second and the third moments. He defined a mollifier, and he showed that we have this good positive proportion. So I want to discuss a little bit what the mollifier method is, because it will be relevant for what I'm going to say next about cubic characters. So mollifiers are very useful. For example, they were used by Selberg to show that a positive proportion of the zeros of zeta lie on the critical line. And the idea is the following. So in the context of quadratic L functions, what Sound did is the following. So we want our mollifier to be defined by some Dirichlet series. And in some sense, we want our mollifier to behave like 1 over the L function. So recall that the first moment grows like x log x if we don't have mollifiers, and the second moment grows like x log x cube. So what we want to do is to define this mollifier so that both the first mollified moment and the second mollified moment are of constant size. So you think of the mollifier as being roughly 1 over your L function, and you want to compute these two mollified moments. If your mollifier is like 1 of your L function, then intuitively speaking, if you want it to be given by a Dirichlet series, it should be given by a sum over a parameter, let's call it L. We have the quadratic character here, chi d of L. We divide by square root of L, because we're looking at the moment at the point 1/2. And we want to throw in the Mobius function to take care of the cancellation. And we let the parameter L grow. It cannot grow too much because we can't have our Dirichlet series to be too long. In fact, the longer Dirichlet series we have, the better proportion of non-vanishing we have, but it cannot be too long because then it becomes unmanageable to compute the moments. So it turns out we can go up to roughly x to the 1/2 in the Dirichlet series for the mollifier. And with this rough choice of mollifier, it's not exactly that, but with this sort of shape of mollifier, we can show that the first and the second mollified moments have size x. And then using Cauchy-Schwarz again, we get the positive proportion of non-vanishing, which is 87.5% for the family of quadratic L-functions. So that's a very good proportion. Any questions so far? Okay, so let's move on to cubic L-functions. Here again, we're interested in these non-vanishing results. So if I look at the family of L-functions associated to cubic characters, can we say something about the values of the L-functions at the point 1/2? So again, let us look at the moments first, because they give us interesting information about non-vanishing. So here we want to compute the kth moment of L1/2 chi, where chi is a cubic character, modulo q. So this means that the third power of chi is the principal character. And I also want to sum over the parameter q. So q, which is the conductor of the character, will go up to x, size x. And again, the star here means that I'm summing over primitive characters. And the conjecture due to Conry, Farmer, Keating, Rubinstein, and Snaith. So this is the analog of what I mentioned before for quadratic characters, but in this cubic context. The conjecture is that these moments are asymptotic to some constant times x. And then we have some power saving error term. Now, in terms of rigorous results, we can say much less than we can in the quadratic case. So in the quadratic case, essentially, we can compute the first 4 moments. For cubic characters, the first moment can be computed rigorously. This is work of Baier and Young. So Baier and Young considered the smoothed first moment. So here we have some weight function W. So in the theorem of Baier and Young, essentially, the conductor Q goes up to size X, and they get some main term of size X, which was to be expected, and then some power saving error term. Now, in terms of non-vanishing, unfortunately, in this family of L-functions, we don't know how to compute the second moment, so we can't use it to get some information about non-vanishing directly. So instead, Baier and Young get an upper bound for a higher moment of in this family of L-functions, and they show that the number of primitive cubic characters with conductor of size up to x, for which the L-function is non-vanishing at the point 1/2, is bigger than x to the 6/7 minus epsilon. So that's quite far from a positive proportion. In fact, if you assume something like the Lindelof hypothesis or the Riemann hypothesis, you would be able to show that more than x to the 1 minus epsilon of these values are non-vanishing, but you wouldn't be able to get that some constant c times x of them are non-vanishing. So our goal in what I'm going to talk about, so we will prove some positive proportion non-vanishing result for the family of cubic L-functions over function fields, but the ideas are transferable to this number field setting as well, but the results would be conditional on the generalized Riemann hypothesis. So before describing the function field results, I want to give a little bit of background on function fields for those people who are not working on that. So here we work with FQ of T, the polynomials with coefficients in FQ. And there's usually this nice dictionary between the integer setting and the function field setting. So we can think of positive integers in analogy with monic polynomials. Then the absolute value of an integer would correspond to the norm of a polynomial. That's defined to be q to the degree of that polynomial, We can think of primes in analogy with monic irreducible polynomials and so on. And then many of the objects that we care about over Q, we can define them in this function field setting. So for example, the zeta function will be defined. So when the real part of S is bigger than 1, the Riemann zeta function is given by the Dirichlet series of 1 over n to the s. Now we want, since positive integers correspond to monics, we want to define the zeta function as the Dirichlet series of 1 over the norm of f to the s, where we're summing over monics. And we know how to count monics of a given degree. If we look at monics of degree n, there are q to the n such polynomials. So this becomes a Dirichlet series, and it's just 1 over, this becomes a geometric series, and this is just 1 over 1 minus q to the 1 minus s. So it has a simple expression, and notice that we have a pole when s is equal to 1, and there are no zeros. And in fact, for this function field setting, it's usually more convenient to work with the variable u, which is q to the minus s. In that case, the zeta function is given by the series of u to the degree of f when we're summing over monics, and the zeta function will just become 1 over 1 minus qu. So it has a simple pole at 1 over q. Okay, so now we want to also define our L functions. These will be defined similarly to the number field setting. So if we have a primitive character modulo h, some polynomial, then the L function associated to the character is defined by the series, so L of u chi will be the sum over monics of chi of f u to the degree of f. That's exactly what you would expect. And this has an Euler product as well over monic irreducible polynomials p, which don't divide h. And it turns out that these L functions in the function field setting have some very nice properties. So if chi is a primitive character modulo h, in fact, it turns out that the L function is a polynomial whose degree is at most the degree of the conductor, so the degree of h minus 1. It has a functional equation, so we can relate L of s chi to L of 1 minus s chi bar. And with the u notation, this means that we can relate L of u chi to L of 1 over q u chi bar. And here in the functional equation, we have this object omega of chi. This is the root number. It has absolute value equal to 1. And I will get back to this object later on in the talk. It will be very important for our computations. Now another nice property of the L function is that in fact the generalized Riemann hypothesis is known in this context. So we know that all the non-trivial zeros of the L function lie on the circle of radius 1 over square root of q. So this is why our results over function fields are unconditional. And if we were to transfer our results in the number field setting, they would be conditional on the generalized Riemann hypothesis. Okay, so what can we say about non-vanishing of cubic L functions, or more generally, non-vanishing of L functions over function fields? So a natural question is Chowla's conjecture true over function fields? So let me remind you that Chowla's conjecture said that if I have some Dirichlet character chi, then the L function is non-vanishing at the critical point 1/2. So in the function field setting, if we focus on quadratic characters, I showed a few years ago in joint work with Hang Bui that more than 94% of the central values are non-vanishing. And we did that not by considering moments, but by computing the so-called one-level density of zeros in the family. So I'm not going to define exactly what this is. Basically, when you compute the one-level density of zeros, you're looking at zeros in the family of L functions, which are close to the critical point 1/2. And studying those zeros tells you something about non-vanishing at the point 1/2. So we have this good proportion of non-vanishing, 94%. But one interesting thing is that in this function field setting, it turns out that Chowla's conjecture is not true. So Wan-Lin Li showed that if you look at quadratic characters whose conductors, the size of the conductor goes up to x, then in fact we have vanishing for more than roughly square root of x of these L-functions. So this is a small number of them. It's still expected that 100% of the L-functions are non-vanishing, but it's interesting that apparently in this case it does happen that they can vanish. And she has a very geometric construction to show, to actually produce these characters for which the L-functions vanish. Okay, now what can we say about cubic L-functions? So again, using geometric techniques, Ellenberg, Lee, and Schusterman showed last year that more than q to the g over square root of g of these L values are non-vanishing. So we would like to say that more than some constant c times q to the g of them are non-vanishing. Now, if we try to compute the one-level density of zeros, this is the approach which yielded the 94% proportion for the quadratic L-functions. It turns out that that approach completely fails. And it's somewhat surprising because for many families of L-functions, computing the one-level density of zeros gives the best proportions of non-vanishing that we have available. However, for this family of L-functions, it doesn't work. So we have to do something different. And the main result that I will talk about today is that we do have a positive proportion. So in joint work with Chantal, David, and Mathilde Lalin, we considered the setting where Q, so the size of the finite field, is an odd prime power, which is congruent to 2 mod 3. This is the so-called non-Kummer setting, when we don't have the cubic roots of unity. And we showed that the number of primitive characters of order 3 with conductor of degree g, that's bigger than c times q to the g for some explicit constant. So the size of the family in this case is q to the g, that corresponds to x in the number field setting. So our results, we proved our results when q is congruent to 2 mod 3. We can prove the same result when q is congruent to 1 mod 3. The details will be pretty similar. That's the so-called Kummer setting. And as I said, the results are transferable to the number field setting as well. The same ideas should work, but the result will be conditional on the generalized Riemann hypothesis. Okay, so how do we prove our result? We can't compute the one-level density of zeros, so we go back to computing moments. And I will explain in a bit what it is that we do exactly. But it will rely on some previous work with David and Lalin on computing the first moment in the family. So last year we showed that we can compute the first moment of cubic L-functions over function fields when q is congruent to 2 mod 3, so the non-Kummer case. Here I have, I'm summing over chi primitive cubic. I wrote that the genus of chi is G. This roughly means that the degree of the conductor of chi is G. And we get an asymptotic formula with the main term of size q to the g and the power saving error term. Now, if we were to use upper bounds for the second moment, we would get that more than q to the g times 1 minus epsilon of these L-functions are non-vanishing. So this is the equivalent of x to the 1 minus epsilon. So we want to do something better than simply using upper bounds for the second moment. So what is the strategy? Well, computing the second moment in the family is open. We don't know how to do that. So we can't compute the second mollified moment. That's even more difficult because we're throwing in the mollifier, so we're doing something extra. But the idea is that if we want to get a positive proportion, it's enough to get a sharp upper bound for the second mollified moment. So in fact, we don't need an asymptotic formula for the second mollified moment. It's enough to get a sharp upper bound. So the strategy is to define some mollifier m of chi so that both the first and the second mollified moments are of size q to the g. So we want to define this mollifier so that we can compute the first moment and so that the second moment is bounded sharply by q to the g. Then if we use Cauchy-Schwarz, we will get that we have this positive proportion of non-vanishing, which is the ratio between the two constants that we get in the asymptotic and the sharp upper bound for the mollifier. Okay, so the main thing is that we want to define this mollifier in such a way so that the second mollified moment is bounded sharply by q to the g. So that's one of the main things. And to do that, we combine ideas from previous work of Soundararajan, who obtained almost sharp upper bounds for moments of the Riemann zeta function. And his ideas were later refined by Harper, who obtained sharp upper bounds for moments of the Riemann zeta function. And more recently, Lester and Radziwill obtained sharp upper bounds for the mollified moments in the family of quadratic twists of modular forms. So these are all different families of L-functions, and all the results are conditional on RH or GRH. And we combine ideas from these papers in order to define our mollifier and then to show that the second mollified moment is bounded by q to the g. Okay, so I want to first discuss this sharp upper bound, and then I will discuss the other part of the proof, which is somewhat independent, and that's obtaining the asymptotic for the first mollified moment. Okay, so the starting point here is an inequality for log of the absolute value of the L function. So we can bound the logarithm of the absolute value by essentially a sum over primes. So here we have a sum over primes with degree up to n, and we have the character, roughly the character over square root of the norm of p. Then we have this second term over here, 1/4 times the sum over primes of degree up to n over 2. And this is the contribution from primes square. From now on, I will just ignore this term. It won't be very important in our computations, but you have to deal with it. And then you get this other term, g over n over here, which essentially comes from the tail. And the O of 1 incorporates all the higher powers of primes, so the third power and higher. Okay, now if you think of n, so the point where you truncate, if you think of that as roughly, let's say g over some big constant, g over 1,000, then your L function will be bounded by the exponential of the sum over primes. Okay, so I'm ignoring the primes square, so this term over here. And the g over n will just be a constant, okay? So essentially I'm looking at the exponential of this sum over primes, and I want to work with that. So what can we do? Well, if we have the exponential, we can think of bounding it in terms of its Taylor series. Okay, so if we look at, let's say, t, which is less than L over E squared, and L is some even parameter, then we have this inequality over here, which gives a bound for the exponential e to the t in terms of its truncated Taylor series. Okay, so we essentially bound e to the t by the sum of t to the s over s factorial when s goes up to L. Okay, so if we are to use this truncated Taylor series for the exponential of the sum over primes over here, what would we get? Well, we would roughly get sums of the following form. So now we sum over polynomials f, whose primes all have degree less than n. Here I have omega of f is less than or equal to L, so omega of f is the number of primes of f counting multiplicities. We roughly get chi of f. We have this omega nu of f, which is just some multiplicative function which comes from the combinatorics of expanding this term. And we divide by square root of the norm of f. So roughly I think of this term n minus the degree of p over p to the 1 over n times n. We just sort of think of this as 1 all of the time in this talk. It's, this factor is not that important. Okay, so we roughly have sums of this form. So now keeping in mind that we want our mollifier to act in some way like 1 over your L function, you might be led to define the mollifier as the sum over all these polynomials f with these conditions that all the primes of f have degree less than n and have less than L prime factors. And we throw in the Liouville function, lambda of f. So that would take care of the cancellation. So the Liouville function is defined to be -1 to the number of primes. So here I could have, for example, the Mobius function mu of f, but lambda is completely multiplicative. So in some sense, it's more convenient to work with it. Okay, so if we define the mollifier in this way, what do we get? Well, we would get that the second moment is bounded by q to the g times log g to some constant power. Okay, so this is not quite what we want. We want to get sharply q to the g. So we have to refine this argument a little bit. So for example, when Sound considered sharp upper bounds for moments of the Riemann zeta function, he split his primes into 2 intervals. So let's try to do that. We split our primes into intervals I0 and I1. By splitting the primes into these intervals, I mean that the degree of the primes are in these intervals. So we have this shorter interval I0 and this bigger interval I1. And we define our parameters L0 and L1 differently. So these are the number of primes on each interval. And then in some sense, we're mollifying each piece. Okay, so we would have that our mollifier is a product of 2 pieces, M0 and M1. And here the MI is mollifying the contribution of the primes in either I0 or I1. Okay, and we define each piece having the toy model that I described before in mind. So we would have that this is a sum over polynomials f whose primes have degree less than n. They have at most Li primes, and we have this Dirichlet series. So the Liouville function times the character, then this multiplicative function, and we divide by square root of the norm of f. Okay, so if we do that, how can we bound our moment? So if the contribution from the primes in the first interval is big, let's call this set T0, we will basically use that this doesn't happen too often. Okay, so I0 contains primes which are not too big. So we expect that contribution to be relatively small, and it cannot be that it's big too often. So basically we will exploit the fact that the size of T0 is small to get that the contribution from these special characters is small. So how do we do that? Well, we upper bound our moment, our average over T0, by the sum over all characters, and we multiply by e squared over L0, and then we have the sum over primes, and we raise that to the power of 2a for some suitably chosen parameter a. So here the point is that we can compute moments of this sum over primes, and because the sum is short, we're stopping at roughly g over log g, we can pick this parameter a to be pretty big. So that will help us. And choosing this parameter a, so the power to which we raise our sum over primes, choosing this parameter suitably, we will show that the contribution from T0 is indeed small. So it's little o of q to the g. Okay, so then we assume that the contribution from the primes, from the small primes is small, and then we move to the next interval I1, and we proceed just as before. So if the contribution from I1 is big, then we do the same trick of multiplying by the sum over primes and raising it to some power. If the contribution is small, then we just use upper bounds for that. And if we run this argument, we will get an upper bound of size q to the g times log g to some constant power. Okay, so this is still not exactly what we want, because we want to get q to the g, but it's already better than what we had if we just considered the sum over primes without splitting it. So before we had q to the g times log g to the big O of 1, and now we have log g to the big O of 1. So we can sort of see now where this is going. If I am to split my primes into 3 intervals, I will get a q to the g times log g to the big O of 1. So in order to get the q to the g, then we roughly want to split our primes into log g intervals. Okay, and this construction is similar to the one in Lester-Radziwill, where they look at quadratic twists of modular forms. So we have roughly log g intervals. We have these parameters Lj, these are the number of primes, and we're mollifying each sum over primes by mj of chi. And this is defined sort of how we would expect from the toy problem that I presented before. Okay, so on each piece, mj of chi will be the sum over polynomials f, whose primes all belong to the interval ij. And f has at most Lj primes. And here we have the character, we have the Liouville function, which takes care of cancellation, and we have this combinatorial function here. And then our mollifier will be the product of all these pieces. And we proceed exactly as before. So if the contribution on I0 is unusually big, then we will take advantage of the fact that that doesn't happen too often. And we will show that that contribution is small. Then we assume that the contribution on I0 is suitably small, and we move on to I1. And we repeat this argument log g times. And this will allow us to get rid of those extra factors that we had in the upper bound. Okay, so I want to make a few remarks on the constant. So the constant is completely explicit. However, we get a really large constant. So the upper bound for the second moment is q to the g times e to the 182. So if we are to use Cauchy-Schwarz and we combine this with the asymptotic for the first mollified moment, then we roughly get the proportion of non-vanishing of e to the minus e to the 182. So this is really tiny, especially compared to the 94% that you get for quadratic characters. And sort of the size of this constant is embedded in the method of proof. So you can't really get something better than e to the something. So for example, when Harper proved sharp upper bounds for moments of the Riemann zeta function, if you look at the kth moment, he also got some constant which has size e to the big O of k. So it's kind of embedded in the method. We can't really do better than that. So we tried to optimize our constant as much as we could. And I'm sure there are still a few places where there is a little bit of room to spare, but the constant is never going to be dramatically better than this e to the 182, even if you work much harder. So it's always going to be e to the something pretty big. Okay, so this was the part where we get the sharp upper bound for the second mollified moment. Now, the other main ingredient is getting the asymptotic formula for the first mollified moment. So once we have this, this mollifier, m of chi, which I defined before, we want to compute the average of L of 1/2 chi times m of chi. And writing m of chi, so writing that as a Dirichlet series, we essentially have to compute a twisted moment, twisted first moment. So we're summing over chi, and we're multiplying the L value, L of 1/2 chi, by chi of h, where h is some polynomial which has small enough degree. Okay, and this comes from the chi of h comes from the mollifier. So to do that, we build on our previous work on just computing the first moment without the twist. And from now on, I will just assume that the twist is 1. So we'll just explain how to get an asymptotic for the first moment without the twist. Okay, so let me give a little bit of background. First of all, how do we define cubic characters over function fields? So let's say that now we are in the Kummer setting when Q is congruent to 1 mod 3. This means that we have cubic roots of unity in FQ. Then we will fix an isomorphism between the cubic roots of unity in C and the cubic roots of unity in FQ. And then if we have a monic irreducible polynomial P, and some polynomial a, then our character will be equal to 0 if p divides a. Otherwise, we know that a to the norm of p minus 1 over 3 modulo p, that's congruent to a cubic root of unity in fq. We want our character to be complex, so we look at the pre-image of that cubic root of unity in fq through this map omega, and we get some alpha, an alpha, which is a cubic root of unity in c, and we define our character chi p of a to be equal to this alpha. Okay, so this is our cubic residue symbol, and we extend it multiplicatively. And this is defined when q is congruent to 1 mod 3. Okay, but now recall that we are working in the non-Kummer setting when q is congruent to 2 mod 3. So that's the equivalent of working over q when you don't have cubic roots of unity. So the question is, how do these cubic characters, primitive cubic characters over fq of t look like when you don't have the cubic, when you don't have the roots of unity, the cubic roots of unity? It turns out that you can parameterize these cubic characters in terms of cubic residue symbols in a quadratic extension of fq of t. So essentially, you can express the cubic characters over fq of t in terms of the cubic residue symbol in fq squared of t. Okay, so here I'm working in fq squared of t. And I have that my character is primitive. So now the conductor capital F will be square free, and it will have this property that it has no primes, no prime divisor in fq of t. So all the primes are in fq squared. Okay, so then I can rewrite my moment over primitive cubic characters in fq of t as a sum over elements in fq squared of t, here, square free with this, these extra conditions. Okay, then the next step is pretty standard. We use the approximate functional equation. So the L function, since the character has genus G, the L function is a polynomial of degree roughly G. So what the approximate functional equation allows us to do is to truncate at some point A, where A is less than G. So we have this main term here, M1. So this is just the Dirichlet series of the L function. And then the dual term will go up to roughly G minus A minus 1. So when we sum them up, we roughly get G, which is the degree of the polynomial. Okay, and here in this second term, this is the dual term, we have this object, omega of chi f. This is the root number that appears in the functional equation. It has absolute value equal to 1. And I will get back to this a bit later. Okay, and the strategy is to get asymptotic formulas for both M1 and M2. M1 will be much easier to work with than the dual term M2, which involves the root number. And they use completely different methods. Okay, so to evaluate M1, you can sort of guess, since you have a cubic character, you can sort of guess that the main term should come from these polynomials h in here, which are cubes. Okay, so if h is a cube, then chi of h is equal to 1 whenever h and the conductor capital F are co-prime to each other. So we compute the contribution from these cubes, and that's not hard to compute. It's a pretty standard computation. We get this main term of size q to the g, q to the g plus 2, and we have this lower order term here, q to the g of size roughly q to the g minus a over 6. So notice that this depends on capital A. This is the point where I'm truncating over here in the Dirichlet series. And of course, we shouldn't expect such a term to appear in the final asymptotic formula, since it depends on this parameter that I can choose no matter how I want. So the strategy will be to show that there is some cancellation between this main term M1 and the dual term M2, so that this term of size q to the g minus a over 6 cancels out. Okay, so now when we look at M2, I rewrote it over here. We have the root number. okay, from the functional equation, it turns out that the root number can be expressed in terms of cubic Gauss sums, and these cubic Gauss sums are very important in our computations. So how are they defined? They are defined similarly to the number field setting. So once you have the exponential over function fields, so here the exponential is defined in the following way. If you have a Laurent series with coefficients in FQ, then E of A is e to the 2 pi I times the trace of A1 over P. A1 is the coefficient of 1 over X in the Laurent expansion of A. Then the cubic Gauss sum, let's say G of VF, this will be a sum over U mod F, and we have the cubic character chi F of U times the exponential of E of UV over F. And it turns out that we can express this root number, omega of chi F, which has absolute value 1, in terms of the cubic Gauss sum associated to the polynomial capital F. Okay, so then if I use this expression for the root number, I can rewrite my dual term in this way. So now the important part is over here. We're summing over this, this parameter capital F, and we have the average of G of HF. Okay, and we're summing in the second variable. So we have to study some of the properties of these Gauss sums, cubic Gauss sums. It turns out that they are quite nice. So they are almost multiplicative. This means that if I look at G of V and the product F1 times F2 for coprime F1 and F2, we get that this will be the product of the two G's, G of VF1 and G of VF2. And we have to twist by the character chi of F1, F2 squared. So if I didn't have this character over here, the Gauss sums would be multiplicative. This is what happens for quadratic characters. And this is one of the reasons why it's much easier to work with quadratic characters, because we have multiplicativity. So for example, if you look at the generating series of these Gauss sums, let's say psi h of u, and you're summing in the second variable, capital F, if you had multiplicativity, then you would be able to write down an Euler product for this. So it would be much more manageable. However, for cubic Gauss sums, we don't have multiplicativity. We have almost multiplicativity. So we don't have an Euler product. So that's one of the reasons why it's much harder to work with this function than in the quadratic case. It turns out that we can study its properties by using the theory of metaplectic Eisenstein series. As introduced by Kubota. Okay, so it turns out that the generating series of the Gauss sums is a rational function. It has a pole when u cube is equal to 1 over q to the 4. And what we do is that we explicitly compute the residue of the pole. So that's where most of the work goes into, getting an exact formula for the residue, getting a precise formula. And if we do that, so if we get this precise formula for the residue when u cube is equal to 1 over q to the 4, this allows us to get an asymptotic formula for the dual term. Okay, and we will get that indeed the dual term is exactly what we would expect, so minus the term of size q to the g minus a over 6, which appeared in the first term, in the principal term m1. Okay, so these two terms cancel out, and we get our formula for the first moment with this main term of size q to the g. Okay, so I think I will stop here. This shows how to get the formula for the first moment. We will need to adapt some of these ideas a little bit to get a formula for the twisted first moment. And once we have a formula for the twisted first moment, we can get a formula for the mollified first moment. Okay, so I will stop here. Thank you.